Make personalized recommendations with user-based collaborative filtering. By the end, you will build a simple recommender that finds similar users, spore items they like, and predict a missing rating for a target user. You will see how similarity choices change recommendations and how a small K nearest neighbor selection fits simple production cases. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. User-based collaborative filtering matters because it optimizes matching user preferences, which you can measure with accuracy metrics like precision at K or mean absolute error. It trades off exactness for simplicity, since storing a full user similarity matrix costs memory and lookup time. Practically, it works very well on datasets where many users rate many overlapping items, and it degrades when users are sparse or when you hit hundreds of thousands of users. At a high level, we compare each user to other users, pick the nearest ones, and borrow their ratings to fill gaps. Cosine similarity compares the angle between two users' rating vectors to capture shared taste direction. Pearson correlation measures linear correlation after subtracting each user mean to focus on relative preferences. User-based methods shine for serendipity in dense communities and fail when new users have no ratings. We will build a small pipeline that computes similarities, finds neighbors, compares Cosine and Pearson, and predicts a missing rating for a target user, showing the final predicted value and a ranked neighbor list. This snippet computes cosine similarity between two users over co-rated items. It selects items both users rated, builds their two rating vectors, and then computes the cosine similarity, which compares the angle between vectors to capture common preference direction. The code handles the case where there are no co-rated items by returning a neutral similarity. If you change the minimum co-rated threshold, you alter robustness. Raising it reduces noisy pairs but increases missing comparisons, while lowering it includes weaker signals and may introduce noise. This snippet is the baseline for preference alignment by direction rather than by absolute rating. Now we will mean center ratings and measure correlation. This snippet measures user similarity with Pearson correlation after mean centering. It subtracts each user's average rating from their co-rated item scores and computes the correlation, which highlights whether users go up and down together relative to their own baselines. Mean centering removes systematic user bias, so a harsh rater can still match a generous rater if their relative patterns agree. Changing the mean computation window, or the minimum co-rated count, will change sensitivity. A small window makes correlations noisy. A larger requirement makes them more reliable but sparser. This gives a complementary similarity to cosine, and often improves prediction when users have different rating scales. Next, we will rank the nearest neighbors for a target user. This snippet ranks the nearest neighbors for a target user using cosine similarity. It iterates over other users, computes pairwise cosine scores against the target, filters by any minimum co-rating requirement, and then sorts to produce a top K list. K is the key adjustable parameter here. A small K makes recommendations rely on very close tastes and reduces noise, but it may miss diversity. A large K brings more signal and stability, but it dilutes personalization and increases computation. The output is a ranked neighbor list with similarity weights you can inspect for trust and debugging. Next up, we will reweight neighbors using Pearson to compare methods. This snippet recalculates neighbor strengths using Pearson to compare against cosine. It takes the same neighbor candidates and recomputes their similarity using mean-centered correlation, producing a second set of weights for the same target. Comparing the two weightings reveals whether neighbors align more by direction or by relative pattern. If Pearson increases a neighbor's weight, that user shares relative rating trends despite absolute differences. Swapping or combining these weights is an easy experiment. Changing the similarity choice changes both which items get high scores and the interpretability of the weights for downstream business rules. Finally, we will predict an unrated item using weighted neighbors. This snippet predicts an unrated item for a user using k-nearest neighbors with Pearson weights. It collects neighbor ratings for that item, weights them by Pearson similarity, and computes a weighted average adjusted back to the target scale. The prediction can include baseline corrections like adding the target user mean. The main parameter is k, which controls how many neighbors contribute. Increasing k smooths predictions and improves stability at the cost of personalization. You should also watch for neighbors with zero correlation, which you may want to drop or regularize to avoid divide by zero or noisy influence. Recap. User-based collaborative filtering uses other users to predict what a user will like. Use it when you have many overlapping ratings and you want human-like recommendations. Watch out for cold starts and quadratic scaling as user counts grow. Next step, try tuning K and the minimum co-rated threshold while measuring precision at K and timing. And then, replace the exact neighbor search with an approximate nearest neighbor index to scale up and compare speed versus accuracy. If Practical IR and Python help you, subscribe and watch the rest of the IR videos.